Given, two zero-indexed integer arrays nums1 and nums2, each sorted in non-increasing order. Rule, a pair, I, j, is valid if I equals j, I len, nums1, j len, nums2, and nums1, I, equals nums2, j. Return, maximum distance j, I over valid pairs, 0 if none. Example 1, every valid index pair is written beside the arrays. We check each pair in order, then settle on the pair with the largest gap and read off the answer. The largest gap is 2, from index 2 on nums1 to index 4 on nums2, j minus I is 4 minus 2, so we write output equals 2. Example 2, valid pairs are listed beside the arrays again, here we go straight to the best pair and the answer. The largest gap is 3, from index 0 to 3, 3 minus 0 is 3, so we write output equals 3. We have two arrays sorted from largest to smallest. We pick an index I in the first array and an index j in the second, with j at least as far right as I. We need nums1 at I to be at most nums2 at j. We want to make the gap j minus I as wide as we can. The slow way is to fix I and try every j in the second array. For 55 in the first list, only 100 in the second works. Then we repeat for the next I. If the lists are long, that is on the order of n times m checks, far too slow for a race. Because both arrays are non-increasing left to right, once a j works for a given I, any smaller j to the left still has a value at least as large as we need. So we only care about pushing j further right to grow the gap. Suppose I is on 30 and j is on 10, and 30 is not less than or equal to 10. When we move I forward to a smaller value like 5, we never need to drag j backward, j can stay put or move right to find the next valid gap. Picture two pointers walking forward. J creeps right while the inequality holds. When it fails, we advance I, j never moves backward, so each list is scanned once in the style of a linear two-pointer pass. Whenever I and j give a valid pair, we take j minus I and keep the best answer so far. That yields linear time in the lengths of the two arrays, with only a few extra variables. We place two pointers at the start of the arrays. Index I starts at 55, and index j starts at 100. We also track the maximum distance, starting at 0. We check, is 100 at least as large as 55? Yes. The condition holds, so we note the distance j minus I is 0, and we try to push j further right next. We move j to 20. Is 20 at least 55? No. Because both arrays are non-increasing to the right, nothing past 20 can rescue this I, so we advance I. We move I to 30. At the same j, is 20 at least 30? Still no. We advance I again. Now I is at 5. 5 is less than or equal to 20, but j is still behind I, so the index gap is invalid. We slide j forward until it catches up to I. With I and j aligned at index 2, we walk j forward. 5 is less than or equal to each next nums2 value, so the distance j minus I grows to 1, then to 2. That becomes our best so far. Once j steps past the last index in nums2, the while loop ends. There is no larger j to try, so we stop here with the best distance we already recorded. The pointers only moved forward. The maximum distance we found was 2, in linear time with constant extra space. Time is order n plus m, I and j each move forward only, so we touch each array once. Space is order 1 for the pointers and the running maximum. An alternative fixes I and binary searches nums2 for order n log m time. Function max distance takes nums1 and nums2. Initialize I and j to 0. Set the answer to 0. Loop while both indices are still inside their arrays. Set j to the larger of j and I so j is never behind I. If nums1 at I is at most nums2 at j, we have a valid pair. Update the answer with the gap j minus I. Advance j to try a wider gap next. Otherwise the inequality fails. Advance I to shrink nums1 at I. Return the best gap we found.